Dear student, colleagues, and all the viewers who are watching this program live from Facebook page Physics Adda, I'd like to welcome you all to our webinar. Good evening to all. Hope you are well and safe from Corona pandemic. Today, I'd like to welcome you all through a joint session between our university, Pabna University of Science and Technology, Pabna, Bangladesh, and the Indian Institute of Technology, Indore, India, on a webinar in experimental nuclear physics and high energy physics. And today we have with us here Dr. Raghunath Sahoo, sir, Associate Professor, Department of Physics, Indian Institute of Technology, Indore, India, joining us from Indore through Steamier. And he has already connected with us, so I would like to welcome him in our webinar. So welcome, sir, and good evening to you.
Yeah, good evening.
So it is a very special day for our department as we're witness such a beautiful program, and it is a memorable day for our department also. And I'd like to say thank you again on the behalf of the Department of Physics, Pabna University of Science and Technology. So all we know that we are passing a very difficult time, and all the institutions have been shut down since March due to Corona pandemic, and it's very difficult for us to continue the normal academic program like classes and exam. So for this reason, we have to go the online program, and we have started some online program like online classes, seminar, and webinar. And I'm happy, very happy to share that in those webinar, the scientists from different countries are coming as main speaker, and I think the student are benefited by this webinar because they can directly connected with our speaker. And in that continuity, today we have with us Dr. Raghunath, sir. He's an experimental nuclear physicist and experimental high energy physicist. He's currently working as an associate professor in the Department of Physics, Indian Institute of Technology, Indore. And you have already come to know that we have arranged a series of webinars. So, and I think this is one of the best webinar in our this season, because you know that today our speaker will talk about our CERN experiment and its benefit to our social impact. So those who are new, I'd like to remind you all that in our webinar, we have divided our session into three parts. First, I'd like to introduce our speaker with all of you, and then there is a session where the speaker will deliver his speech, and in the final session, there is a time for discussion, and in that time, anybody can join with us directly, and if you have any question, you can ask by commenting in the Facebook. So let's go to our first session, introduction to our speaker, to all of you. So you have already come to know that our today's webinar title is Societal Benefit of Big Bang Collision at the Large Hadron Collider CERN. And our speaker is Dr. Raghunath Sahoo, Associate Professor, Department of Physics, Indian Institute of Technology, Indore. So he is currently working as an associate professor, Department of Physics, Indian Institute of Technology, Indore. And if we see his academic background, so he has completed his master's degree from Utkal University, Bhubaneswar in particle physics. And then he completed his PhD in 2007 from the Institute of Physics, Bhubaneswar. And then he joined as a research scientist at the University of Cape Town at May 2007, and then as a visiting scientist at Institute of Physics, Bhubaneswar. And then he joined as a postdoctoral fellow at CNRS. And then there is another postdoc fellow in INF fellow at Padova, Italy. And he also got a fellow award from the Institute of Physics, UK. Professional experience, if we see his professional experience, so he has started his career as a visiting professor at the Indian Institute of Management, Indore, and then as an assistant professor in Indian Institute of Technology, Indore, and then now He joined as associate professor at the same institute, and he actually working as an associate professor from 2013. Professor Sahoo is an associate professor in experimental high energy physics, and he earned his PhD in experimental high energy physics from Institute of Physics, Bhubaneswar, and working in the STAR experiment at the relativistic heavy ion collider. So, if we see more about his professional experience, he was a visiting scientist at IOP. I have already uh, talked about that, and he also working as a Bukhaba National Lab as a subtech, and actually he got two postdoctoral fellowship, one from INFN and another from maybe from another from that place
CERN.
CNRS. Yeah,
Right.
son. So if we see his academic visit abroad, he has visited a lot of countries like China, Vietnam, Netherlands, Switzerland, Japan, USA, Hungary, South Africa, France, Italy, Germany. And if we see his award and honors, honors, so he have got different awards from INFN Fellow Italy, CNRS Fellowship, and Feinberg Fellowship from Israel. And research group, he is presently the team leader of the principal investigator of the ALICE and CMB and GSI Germany project from IIT Indore. He served as a member in ALICE and CMB collaboration board and a member in ALICE India management board. Professor Sao has been in the ALICE India task force for future physics, in the task force for the bylaws amendment, and has chaired the ALICE India DPR committee for mega science project. And he's one of the few experimental high energy physicists who has a visible contribution to the phenomenology of high energy physics, and with actually 10 PhD and postdoctoral fellow. And that is very actually very good things that we got, and we are really proud that we got the scientists like him as our uh, speaker of our webinar. So Professor Shah has made a visible high energy physics group with the highest publication record in India, and maybe he has a more than 450, about 450. He has as a collaborator, and he has supervised 7 PhD and 11 postdoctoral fellowship, around 42 MS BTech student, leading to around 60 students in total. So research interest, he has a research interest in global properties of quark-gluon plasma, QGP, created in the Big Bang experiment, and exploration of the QCD phase diagram and search for the critical point, matter form at the high baryon densities, phenomenology of quark-gluon plasma, and the gamma ray astronomy PV energy. Seminar, he have delivered lot of seminar in different kind of uh, conference and for awareness for the society also. So if we see his publication, I have already told that he have more than about 450 journal in different international journal, and the research project, he have got different research project from different institution and membership. So if we see his memberships, fellow member Institute of Physics United Kingdom, life member Indian Physics Association, and life member Indian Science Congress Association, and patron member Orissa Physical Society, life member Orissa Bigyan Academy. And if we see his Google Scholar citation number is more than 57,000, and it's very great number actually. And we feel really proud that he actually agree our proposal. And if we see his researchgate ID, you can see his researchgate number is 31.3. So thanks for your patience. Now let's go to our today's speaker. And so, sir, I'd like to welcome you again. So you can start your session, sir.
Okay, so I am a bit excited to deliver this lecture today to Bangladesh. So namaskar to all the audience
Yeah.
who have joined online. And the present pandemic scenario, I think we should engage ourselves in the process of learning and teaching, and you have taken a good initiative. So I am very thankful to Professor Pretam Kumar Das, Padna University of Science and Technology, and thank you for very much for your invitation. And looks like you have done a good homework in introducing me very nicely in a detailed way, going from Google Scholar to my homepage and many other sources of information. So thank you very much for doing a good homework.
But I think I left a lot of things because we have a lot of more things. So the views
I think it is good enough for the viewers, and if I can succeed convincing the viewers, it is worth doing basic science, and yeah, the subatomic domain of science can actually give good societal benefits. So I think I can do my job of contributing or explaining to the general public. So that it is worth doing basic science at the subatomic level. So if you permit me, so I'll go to my presentation, and in case there is any glitch in internet or communication problems, so you can actually stop me in between.
Okay, I'll inform you.
Oh. So you can see my.
It has disconnected, so you need to add again.
So what about now?
So share option may be omitted, so you need to share again. The file have been deleted. Maybe you need to do it again. Dear viewer, we're sorry due to some technical problem. We have disconnected with our speaker. So within short time, we may connect it with our speaker. So stay with us.
Can you hear me now? There was some problem once I.
Okay. Yeah, maybe. Yeah.
So I should share the screen. Share the screen now, and yes. Okay. So can you see my slides now?
Yeah, we can see.
Perfect. So sorry for the interruption. Let me go to now my presentation. Yeah. So since last almost 20 years of working in this frontiers of high energy nuclear physics with the aim of producing a primordial matter in relativistic collisions of heavy nuclei in various frontier laboratories around the world. For example, Brookhaven National Laboratory to the European Center for Nuclear Research, CERN. So I thought it is a social responsibility also to convey the message to larger audience, if at all there is any societal benefits of doing this kind of basic science at the subatomic level. And I took this challenge and I gave this lecture in a couple of places in India. And after getting the invitation from Pabna University of Science and Technology, Bangladesh, I thought it will be a pleasure, because talking to our neighbor countries and trying to encourage the students for doing basic science or the subatomic physics will be really good. So I readily accepted this offer of giving this seminar, and next 1 hour I will try to convince or give the message to you what are the societal benefits of Big Bang collision. And we all know the universe started with the theory. We believe that there is a Big Bang collision. Two hot and huge heavenly objects collided, and the temperature was very high to start with, and it follows a spatio-temporal evolution. And the present the universe is a byproduct or the outcome of the initial Big Bang collision. So the question is, can we create or recreate, in fact, the such a scenario of early universe in the laboratory and study what might have happened at a few microseconds after the Big Bang collision and how this evolution of the universe started. So with this game, the societal benefits comes as a byproduct of doing or addressing the curiosity of humankind. And let's now move ahead. So fundamental science and technology. So if you see accumulation of new fundamental knowledge, development of scientists and engineers, like the way we teach and learn in the classrooms, making good scientists and engineers are the mandates of most of the research laboratories on basic science. And if we ask, the development of new applications is not a formal mandate. So in the universities like Bangladesh and India, we usually do not engage ourselves for the development of application-oriented research, although slowly application has come into our curriculum. So results of basic science do not lead to immediate applications, as I told you, and today's basic science is tomorrow's technology. So once that goes to the domain of applications, slowly technology emerges out. However, explorations in the new domains of basic science require new instruments and hence new technologies. So now research is also highly dependent on advancement of technologies. So if I am allowed to take a couple of examples of basic science, when it was discovered, theory of electricity was just a textbook theory. And if you see, look at the application of theory of electricity, so everything as of today depends upon electricity and electric light and any home appliances you take. So now we cannot imagine a life without electricity. So this has started from basic science theoretical development, or knowing how electricity could be produced, what is the basic underlying theory of electricity. Similarly, the unification mechanism of electricity and magnetism happened through Maxwell's equations. These are taught in the classroom in our BTech or intermediate science classes. So as a byproduct of which electric motors, generators, electrotechnical economy started. And once we started understanding the atomic model, so for example, X-rays, and you can think of application of X-rays starting from medical to security in the airport, in so many areas. So atomic model, understanding the atomic model or the production of X-rays has contributed to. Theory of nucleus has contributed to nuclear energy like fission, fusion, and we know in the nuclear reactors in most of the European and American laboratories, and in India also. I am not aware about nuclear energy program or power program in Bangladesh, but fission is the way we have nuclear energy production in the laboratories. And just to give you a little glimpse, the fusion is another process, like what is happening in the solar inside the sun. In the similar way, we have now started building experimental laboratory, the ITER project in France, where many countries are collaborating. India is one of them. So we are in the process of creating energy through fusion process, what happens actually inside the sun, and we get energy. So if you look at Newtonian dynamics, space science, everything has given rise to space satellites, weather forecast, and telecommunication. So if you look at our eastern side of India and Bangladesh are more vulnerable to Bay of Bengal weather disturbances like cyclone, heavy rain. You can see the weather forecast has been a tremendous success, and this only depends upon the basic science. And the application hub which has gone to the satellite program, and we have weather satellites. So giving and modeling is exact now, and we know what is going to happen to the weather. So before almost a week or so, and then we take precaution. You manage your disaster management program is wonderful now, and we save lots of life. And this has many things to do with the basic science and applications. If you look at general or special theory of relativity, which has given rise to global positioning satellite system like GPS. So traveling from any place or driving, so we exactly we put on the GPS system that guides us, and you just think in the absence of GPS, now things are not really manageable with high population and everything coming to a precision level. And if you can do a simple calculation without taking special and general theory of relativity, you will find that GPS will have almost 10 kilometers error per day. And if I take into account, if general people who do not understand special theory or general theory of relativity, so they will understand that what is there, it is just a basic science, it is a textbook stuff, but it is not. If you look at the application side, so if I take into account special theory of relativity or general theory of relativity, so I can convince you through one-page calculation that global positioning system has accuracy of to 15 meters. If you look at this adverse weather aircraft landing, when things are operated in GPS, automated mode, autopilot mode, you will find everything is just perfect. So you can think that which way this special theory of relativity, general theory of relativity have helped us in GPS system. And nuclear magnetic resonance, this MRI helps us in imaging purposes like brain imaging. Any disorder in the brain can be imaged through this nuclear magnetic resonance. These are actually a couple of examples just to convince you that basic science has tremendous applications in technology, and which has actually contributed for our ease of life. Our ease of life has tremendously benefited from technological development, which are actually byproducts of basic science applications. So if you look at the growth of applications with fundamental science, you will find that abstract fundamental knowledge becomes familiar. For example, while switching on the light or switching on the TV using a remote, people have the impression that they are familiarized with electromagnetic phenomena. You see, any general any general person, so at the user level, we have started thinking that we know everything about electromagnetic phenomena. So anybody going through, let's say, your electromagnetic theory in the classroom, so you could realize how difficult it is or simpler it is to know all the basic underlying theories of electromagnetic theory, starting from electricity, magnetism, combine both and have electromagnetic wave phenomena and transmission of electromagnetic waves in various media. So the message I wanted to give is, with time, this technology becomes very familiar and we never bother to know about the underlying phenomena. So this is a pyramidal structure. I have adopted the pyramidal structure of growth of technology. And if, as you can see, if the base is profound, or solid base is created in terms of our understanding of classical physics, atomic physics, nuclear physics, particle physics, and finally the physics at subatomic quark level, and in the micro domain, the planets, stars, and galaxies. So if the foundation is better, so you will find that the technological development will have a better growth and the pyramidal structure will stand nicely. So this picture I have adapted from the famous book of Lord of Collider Rings at CERN, written by CERN Director General, ex-CERN Director General Harry Soper. And because of these developments, you see, it has taken almost 100 years or so, bringing classical physics or atomic physics to application level, coming to television, or you look at superconductivity, nuclear reactors, or navigation system, or manned space stations. So you look at the space programs of India, France, United States, and many other countries. Those are tremendous success. Now you may wonder, for example, quantum mechanics. So Einstein initially had the idea or belief that God does not play dice. So he was not believing in the theory of probability, which has, your quantum mechanics has basic ingredients in terms of quantum states, which are probabilistic in nature. So John Weyl, a CERN theoretician, he gave rise to entangled quantum states, which are actually, to start with, purely theoretical stuff. If you look at the technological side, on the basis of which new technology of transmitting secret coded messages and its application started in 2007 from public vote in Geneva, in Switzerland. So you sit at home, you can cast your vote, and it is end to end coded. So you can see, when now you are making a WhatsApp message, so you can find that in the first message, let's say you make a message to me, so it says that it's end-to-end encryption. That means anybody cannot actually interfere in between from the transmitter to the receiver. Once it is in electromagnetic form, so decoding it is difficult. That is what it says. And the whole theory is dependent on entangled quantum states. So these have become the basic or essential elements of quantum computers, or next generation computers. So we start with very simple or complicated theories, basic science, and as application of which we get tremendous benefits. And if you know that unification of these forces, weak and electromagnetic forces, for which Glasgow, Shalom, and Weinberg, and the only Pakistan scientist of the Salam, so he was part of the Nobel Prize for unification of weak and electromagnetic forces, and giving us this standard model of particle physics, so which is actually one of the major success of modern physics in the 20th century. And this unification business started from Maxwell uniting electricity and magnetism. And this is standard model of particle physics, which has actually given us the domain to study or find different particles in the subatomic domain. And in the future, nobody knows if this can actually give tremendous applications in the daily life, in the technological front. So if you look at technological spin-offs, research is often limited by what is technically available. So to make progress in fundamental sciences, one needs new instruments, so that we cannot actually ignore. So new technologies depend on fundamental research, because to develop new technologies or instruments, we also should have fundamental research knowledge. Fundamental research also depends on technologies. So there is a symbiotic approach, mutual dependency on each other. Like microscope, tabletop microscope was essential for biology and medicine. To know the structural composition of a blood, we use biological microscope that everybody knows from, when you are sick, you go for a blood test, so we know how microscope helps to understand the structure of or the composition of blood. So Galileo's telescope revolutionized the view of the universe. Starting of the era of observational physics began, from Galileo. So that telescope was quite useful, and the lesson from these is a symbiotic approach of science and technology is necessary in the forefront scientific research to be coupled with technological innovations. Unless we go along with each other with a symbiotic approach with interdependency, helping each other, science and technology, so development will be slowed down. So this is a message that we have to go together, both science and technology. Again, if I remind you, the world before transistors or the vacuum tubes, anybody of my age or higher age, you could have realized that the vacuum tubes, which are used in the radios and televisions, were looking like this. So to make a modern day laptop computer, or for example your iPhone or any pocket telephone now, cell phone, so slowly that time the Intel co-founder Gordon Moore predicted in 1965 that this number of transistors on integrated circuits will double each year. So if you see the graph, which is not a physics graph, of course, it is a prediction. And if you see from 1970 to 2018, so you can feel that, the way the number of transistors inside the integrated circuit has developed. So slowly we enter to a typical transistor of three-leg transistor like this. And just to make you surprise, your Apple iPhone of 6 Plus, why I'm giving this version, because the modern, again, if you go to your 10 version 10 or 11, so those will be again with a higher technologies. So if you look at iPhone 6 or iPhone 6 Plus, it has A8 chip which has 2 billion transistors, and the dimension is 20 nanometer dimension. If you think there are only less than 100 or less than 50 these vacuum tubes inside a radio, which was almost 2 feet, 3 feet long during our childhood days. And if you think of now, our iPhone or any phone inside the pocket having all kind of applications can accommodate 2 billion transistors. You think of almost 60, 70 years of evolution of science and technology. Today, where we are, the older generation can only feel about the technological developments, because last 40 years, last 30 years, or last 70 years, starting from a vacuum tube like this, so we have slowly emerged to a IC era where we can accommodate 2 billion transistors. This is not easily imaginable by the next generation. So by this, I would like to convey the message to the next generation: science and technology have interdependency, and the way you go on developing without stopping at the necessity, like necessity is the mother of invention. Slowly you try to miniaturize things and develop electronics in a way so that your ease of life is better day by day. So if you look at basic science is driven by human curiosity, how and why of things. Like gravitation was discovered by Newton, looking into the freely falling apple. And you see, almost all the countries you may have apple, but never we thought of in our childhood this apple is falling because of the gravity. So an intuitive mind, or how and why of things to understand everything, depends upon human curiosity. Necessity is the mother of invention. Technology gets birth out of basic science and applications. Scientific curiosity, what are the fundamental constituents of matter? This has driven us to look into the basic structure of matter. So as you see, this is the normal matter which we can see in naked eyes. If you look inside, of course, we need uh, uh, high resolution cameras, for example, or microscopes. We start seeing the atomic arrays. This we study in the classrooms. And slowly, if we look into the atoms, we have nucleus. Nucleus has neutron and protons. Electrons are revolving around. And slowly, if you look at constituent of neutron and proton, so we have quarks. So for this, starting from high wavelength, slowly I should use lower and lower wavelength if I want to probe deeper into the structure of matter. So now the whole basic theory depends upon the famous de Broglie small equation: lambda is equal to h over p. If I want to see lower dimension, I need to use wavelength of lower wavelengths, and for which the momentum or equivalently the energy has to be quite high. So this gives me macro, the classical world of normal matter, to the subatomic universe. In this scale, the energy requirement will be very high. This will also convince you why we cannot have, for example, in India and Bangladesh, to study the quark structure of matter, we cannot have experimental facilities like Large Hadron Collider. So if you look here, from normal matter to quarks and gluons, the basic or the fundamental constituent of matter, we have to increase our accelerator energy, and I will now convince you what is the necessity of higher energy. So if you look at cells with the dimensions of few mm, we need microscopes, tabletop microscopes. Slowly, if I will need to understand the DNA structure, I need electron microscope. And if you look at the nuclear structure or nuclear composition, you need particle accelerators, and we have several of them in India, starting from Calcutta VCC Sahoo Institute and Tata Institute of Fundamental Research in Bombay, Institute of Physics Bhubaneswar, Bhabha Atomic Research Center in Bombay, in various places, in Delhi also, Inter-University Center, Accelerator Center. There are several places we have also accelerators. And these accelerators energies are limited by few MeVs. And if you want to go to quark structure or the more fundamental structure or what might have existed at the early universe, at the beginning of the universe, so you will find that the energy requirement will be huge at the level of GV or TV, and a multinational collaboration or a huge establishment like Large Hadron Collider will be essential. So nothing to worry, I will slowly make a transition to Large Hadron Collider. So before this, let me convince you how much high is the high energy. So high energies allows us to look deeper into nature, and this is governed by E is proportional to 1 by size. So this is governed by your powerful microscope. The fundamental principle was given by Louis de Broglie, so one of the Nobel laureates in physics. And to discover new particles with high energies, because we want to probe lower in length scale, we use high energies. By this, we produce many particles in the final state, multitude of particles in the final state. This is governed by the famous Einstein's equation of E is equal to mc square. Although Einstein did not get Nobel Prize for E is equal to mc square, he got it for photoelectric effect. He has immense contribution to modern physics. He is one of the genius physicists in the 20th century. And so next principle, because of high energy, tells us that E is equal to kT, and with high energy, I essentially probe the high temperature domain, and this is governed by again a small and beautiful equation. These small beautiful equations I have written here. This is by Ludwig Boltzmann, who was the pioneer or the father of statistical mechanics. So to probe the subatomic universe, we need very high energies, which could produce many particles, and in the final state, and a very high temperature system will be produced. So these are actually some of the necessities and consequences of going to very high energies. So how do we do that? So a journey from electrons to quarks started after the first discovery of the fundamental particle, who stayed as fundamental till now. It started in 1897 with the discovery of electron as a fundamental building block of matter by J.J. Thomson. And just to excite you, I should tell you that his son also got Nobel Prize, again in proving the diffraction of electron, or proving that electron can also behave like a wave. So both father and son duo got Nobel Prize separately. And you see, in the class textbooks, we know electric field can help us in accelerating charged particles. Magnetic field can help us in bending the charged particles. With the same principle of electricity and magnetism, these cathode rays, which are produced by J.J. Thomson, many people also tried beforehand. So these cathode rays can be accelerated in electric potential and can be deflected in the magnetic fields, and we could see in a zinc sulfide kind of fluorescent screen. So these spots could be seen. So subatomic particles which cannot be seen by our naked eyes, we can devise different kind of detectors and technologies to see these subatomic particles. This was, of course, a simple and tabletop experiment, and it was discovered to be the constituent of normal matter. And as you know, electron stays as a fundamental particle as of now also. And the lesson is, we see electrons with our own eyes using different detectors. The detectors are becoming our eyes slowly in the subatomic domain. So slowly we understood through Rutherford scattering that we have a central nucleus, the composition of which is nucleons, so namely protons and neutrons, and electrons are revolving around them. So this is the fundamental understanding. And just to give you the scale of energy, so if you want to ionize one hydrogen atom, just take out that outer shell electron, you need 13.6 electron volt. To give you a flavor what is electron volt, so you must be knowing if I leave one electron in a 1 volt potential difference, whatever kinetic energy will be gained by one electron, that is 1 electron volt. So you can see the small batteries which we are using in torch are usually 1.5 volt. So this gives us the idea of 1 electron volt as a normal understanding. So the journey from electrons to quarks started slowly in the SLAC Stanford Linear Accelerator Center, which is 3.2 kilometers. I remind you that Thomson's experiment was just tabletop experiment. And if you go to Stanford Linear Accelerator, 3.2 kilometers linear accelerator started with electron-positron energies of the order of 50 GeV. And this was instrumental in giving the deep inelastic scattering and knowing that inside the protons there are 3 scattering centers, which are actually nothing but quarks. UUD and UDD are the quark composition, constituent quarks of proton and neutron. And this also, you can do a simple calculation at what energy is required if you want to probe the quark dimension using the simple formula of de Broglie, for which he got Nobel Prize. And you can take proton charge radius to be 0.843 Fermi, and you will realize GeV and TeV energies will be required. So slowly we discovered families of quarks and leptons. So there are 3 families in particle physics. You will learn, or you might have learned by now. So we have up-down, charm strains, top-bottom, different families of quarks, and leptons, different families of leptons. So these are actually fundamental constituents of matter. Now, before I take you to the domain of strong interactions or quantum chromodynamics, let me give you a glimpse of the differences between quantum electrodynamics and quantum chromodynamics. You know quantum electrodynamics. So if I have a neutral atom, to kick out the outer shell electron, I just need 13.6 electron volt, as I told you. So the message here is the constituents of the atom can be separated out in quantum electrodynamics. If you go to strong interaction, which happens in the nuclear regime, so you will find that this quantum chromodynamics is the essential theory to explain the strong interaction. Now, this is a white proton. White proton means I'm just taking a proton which has no color charge, it is color neutral. You can find these 3 quarks having red, blue, and green as different colors, because quarks come in 3 different colors. If I want to separate any quark, to see the individual identity, the color field or the strong field will grow with the separation, and slowly excuse me. So slowly what will happen is a quark anti-quark pair will pop up from the vacuum. By this, instead of getting individual separation, I will produce another proton with 3 quarks, and this quark anti-quark produced from the vacuum, one anti-quark will be combined with a quark, giving you a meson, which is a pi meson, and one quark will go to combine with other leftover 2 quarks to give you 3 quark combination, which is a hadron or the proton. So lesson here is we cannot have individual identity or pre-quarks. So should I stop our research here, because we have understood individual identity or separating quarks is not possible? So should I stop our research at this point of time that we have understood the microscopic or the subnucleon level, that these are the fundamental particles and individual existence is not possible? So answer, I guess, to the curious mind of scientists, answer should be no. We should not stop at this point. So can we find free quarks? So these properties of asymptotic freedom or infrared slavery, which is actually a fundamental theory of quantum chromodynamics or the strong interaction, was given by Gross, Wilczek, and Politzer. So they got Nobel Prize in 2004. And this QCD predicts that under extreme conditions of temperature and energy densities, normal nuclear matter can undergo a phase transition, producing quark-gluon plasma. So after this, so our journey started to see a 6th state of matter. We know solid, liquid, gas, then Your plasma state is fourth state of matter, and the fifth state of matter is essentially the colored plasma. So can we have a fifth state of matter which is quark gluon plasma, the colored objects? As I told you, these protons or hadrons, this inside hadrons, these quarks are actually caged, means they cannot come out of the hadrons. Now, can I compress the hadrons or melt the hadrons so that beyond this hadronic dimension, I can produce a plasma of quarks and gluons? This is the glorious drive of high energy nuclear physicists, taking us way forward in colliding heavy nuclei by this producing a temperature or energy density which could melt the hadrons, the temperature of which is almost 10 to the power 5 times higher than the core of the sun temperature, so that we can produce a quark gluon plasma phase which can mimic or resemble like the early universe primordial matter. After producing this in the laboratory, we look into the time evolution. So expansion causes cooling. So we studied in our intermediate or before that. So a high temperature object can expand rapidly and it will cool down. Similar way our universe can be formed. So we do this kind of heavy nuclei collision at ultra relativistic energies in the laboratories like relativistic Brookhaven, relativistic heavy ion collider in Brookhaven National Laboratory, US, or in CERN laboratory in Geneva, Switzerland. And India is a participant, active participant, both from accelerators, detector development, and in the tremendous goal of doing physics. We have immense contribution in doing physics in this domain of high energy nuclear physics. So a journey to the beginning of the universe started. So this was a schematic of the Big Bang collision I explained you. And after the collision with very complex processes, dynamical processes, the evolution of the whole universe started, and we stand here as of today. As you go to the left, the energy scale will increase and the temperature scale will also increase, and slowly we go to few microseconds after the Big Bang in the laboratory to create such a scenario. Now, to convince you or to excite you in the domain of physics on which nature operates, you will be astonished to know that 10 to the power 60 is the scale or order of magnitude in which nature operates. From micro to macro state, you will calculate. It's a simple calculation I'll give you now. So the nature operates in the scale of 10 to the power 60. And the tools and methods to probe the nature depends on the length scale being probed. You want to see the atomic structure, let's say atomic arrays, you can use a transmission electron microscope and you can accommodate that on a tabletop experiment. But if you want to go to the quark domain, of course you need big accelerators the way I have shown you. And in that domain, if you see in the microstate, the scale of 10 to the power minus 34 to, if you go to the domain of radio telescopes used for observing the radius of the universe, 10 to the power 26 scale, so it's almost 10 to the power 60 scale. Nature is beautiful, it is tremendous, and we have not probed everything, and still the research in different domains are on. And just to excite you, we are actually in a general perception, we are limited to 10 to the power 10 order of magnitude in the world of middle dimensions. For example, if you take your length, mass, and time as the fundamental dimensions, for example, if you take length, how minimum length you can see in your naked eye, and what is the maximum length you can see in your naked eye. So you go to, in a clean sky, you go to a table, to a mountain top, you can see few kilometers. Few kilometers means, let's say, maximum 100 kilometers you can see. So that takes you to 10 to the power 2. And similarly, if you go to the lower scale, so micron scale also you cannot see, the fraction of your hair dimension you can see. In similar way, if you calculate lengthwise, almost 10 to the power 10 order of magnitude you can see in your naked eye. Similar calculations also you can see for time and also for mass. So you will convince yourself that this scale of middle dimensions is limited to 10 to the power 10, our human perception level. And beyond this, for example, going to lower micro scale or going to the macro scale. So we need instruments. And this is what the instruments I show you, starting from particle accelerators to the radio telescopes. So this is the beauty of the universe. It operates in the 10 to the power 60 order of magnitude, and we need various instruments. This is where both technology and basic science have interdependency. So nature in its full glory, from microcosm to cosmos, we need Large Hadron Collider kind of experiments at CERN. This is a 150 meters underground, 27 kilometers circular collider, and the tunnel of 4-meter diameter. You can see one can actually take a car and ride here for not for fun but for repairing of the instruments, and it is built to 0.1 millimeter per kilometer precision. So meaning is both mechanical, electrical engineering, civil engineering, everything has a precision, and this is a tremendous success at the Large Hadron Collider. If you look at the other scale of the cosmos, we have Hubble telescope, which is around 50 square meters, more than 500 kilometers above the Earth's surface. So these are two different ways of looking into the universe. One is micro, another is the cosmos. One is microcosmos or microcosm, another is the cosmos in the large scale, and another the small scale. So why collider experiments? So if this collision is like a fixed target collision, so that's a tree and a car is coming and colliding by mistake, the damage level is a bit less. If you look at a highway, two speeding objects like two cars colliding with each other, damage level is high. So meaning here I want to tell you is, we look into the debris produced to know what kind of fundamental constituents these objects are made up of. So with the same philosophy, in the laboratories, what we do is we prefer colliding beam experiments where the beam of 440 GeV can collide, giving me 900 GeV energy. If you look at fixed target experiments, so the beam energy of 450 with a fixed target can give me center of mass energy of 19 GeV. Compared to 900 GeV, my 29 GeV is very small. So meaning here is, we should go to a collider mode of experiment, make collision of ultra relativistic heavy nuclei to produce the primordial matter in the laboratory. So I think I could convince you why a collider experiment is necessary compared to a fixed target experiment, which is actually the precursor of the collider experiment. So this is the way two Lorentz contracted heavy nuclei, they are contracted in the longitudinal direction, in the collision axis. It is contracted, as you can know from Einstein's special theory of relativity. This is actually collision of two heavy nuclei. After that, production of many particles in the final state is happening. And so these Lorentz contracted heavy nuclei, after the collision, they possibly produced a pre-equilibrium stage of quark-gluon plasma, the partonic matter or the quarks and gluonic matter. Then they go through hadronization, giving you a hadron gas. Here we apply our statistical mechanics and other principles which we learn from our textbook. Then this goes through different kind of complex processes. As you can see, these are the particle tracks in our detectors, which we have in Alice experiment and in other experiments in the CERN laboratory or high energy physics laboratory. This is the way, starting from the collision till the particle tracks, and you can see this filtering of the tracks and identifying these tracks as different particles, subatomic particles like pions, kaons, and protons will be a difficult job, of course. And for this, high level of computing power, computing algorithms will be required. So this involves many different attributes of science and technology. So this is how matter produces, or energy produces matter and matter produces energy using E is equal to mc square. This is very simple cartoon that I collide two strawberries, produce energy, and this energy can produce many different fruits like pears, apples, orange, banana, and also since Bangladesh is famous for peace, particularly Hilsa, and I had a good discussion with Dr. Das yesterday. So this energy can produce also any object, and it is mass, and peace can also be produced. And in the famous visit of the Pope of Vatican City, looking into this picture, the Pope told that creation should be restricted to the God. So let's strike out creation and just say that it is production of matter. So different matters can be produced out of energy, and this energy can also be created from mass. So this is a beautiful cartoon explaining production of mass out of energy. Okay, so the right way to look is, we know what is the basic principle on which vision works. We can see any object using a lamp. So let's say I put a torch light with a visible wavelength light. Once it is scattered from any object and the scatter light is coming to my eyes, I can see the object. Exactly in a similar fashion, or with the similar physics, underlying physics, the detection at subatomic level works. So we have accelerators similar to the lamp giving light, and the light analogy here is the particles, and the wavelength created will depend upon the momentum. And you can see after this the particles are scattered through the objects, the scattered particles can be detected by our detectors, which are our eyes, and I can see this subatomic particle. So with the same philosophy or underlying physics of seeing particles, so we go to the different kind of accelerators, and I explained to you that this is the concept of energy of one battery, and at Large Hadron Collider we need almost 2 times of 7,000 trillion batteries. Some understanding of mass and energy, we use the units in an interchangeable way, mass and energy, following Einstein's E is equal to mc square formula. And when I say it is 1 MeV, it is 1 mega electron volt, which is a million electron volt. And at LHC, we work at almost 1 TeV, few TeV energies, which is 1 trillion electron volt. These are the units in high energy physics or high energy nuclear physics. So this will be a dream almost, if I do not give you a flavor of your known mass, how does that resemble with these energies? Just to give you a flavor, electron mass is 0.5 MeV, proton mass is 1 GeV around, because 938 MeV is the mass of proton. And the God particle, which was discovered in 2012 in this laboratory, so this mass is around 125 GeV. So this will give you a flavor of energy at which we are working, this tera electron volt. So again, nothing to be worried about accelerators, because the old television sets were using accelerators. So we have cathode rays being accelerated in the electric field and bending in the magnetic field, and we have certain kind of screens which are giving me the pictures. So I can actually translate the simple principle of a television to a complex accelerator environment, and LHC is one of the next generation accelerators. As you can see, there are linear accelerators and then circular accelerators. Slowly the size of the circle increases, taking us to 27 kilometers, 150 meters underground accelerator. So this is Large Hadron Collider, and you may question, or you may start thinking how these circles are associated with energies, and why I need bigger and bigger circles if I want to go for high energies. So this gives a picture of Large Hadron Collider experiment. Various experimental facilities are there: ALICE, ATLAS, LHCV, CMS. India is a stakeholder in ALICE and CMS experiment, and as you can see, it is 27 kilometers spanning the French and Switzerland borders, and you can see Geneva Lake here, and Geneva Airport is here. Okay, so we land here and we go to take part in this experiments in ALICE. So I am involved in ALICE experiment, and this is an underground experiment. As I told you, almost 150 meters underground. So this is a next generation detector. So when I talk about small detectors in your laboratories, you might have seen scintillator detectors or other different kind of detectors which are very small in dimension. If you look at the detectors used in the next generation, your subatomic scale particle detection, you will find one of the detectors is Atlas detector, which was responsible for the God particle discovery. You can see a person is standing here. So you can see the scale. It is almost like 6-story building. You will be astonished to see the scale of the experiment, scale of the detector. So this is again the CMS detector. India is a stakeholder, and some of the detectors here are actually made in Bhabha Atomic Research Center and Tata Institute of Fundamental Research in Bombay. And you can see a person standing, and believe me that making these big detectors are completely driven by physics principles. Why I should make this much big detector? It is just not a fun or and as you can see, as I told you, that multitude of particles will be produced in the final state. Each particle detection, like it is a gamma ray or it is a pion or it is a proton, so the detection principle is different. For example, each country is involved in a detection of a different kind of particle, and sometimes it is multinational collaboration. This gives rise to many people involvement in these big experiments. So this is another detector dedicated for study of the primordial matter, which is called quark-gluon plasma. And this ALICE detector is where India is involved, and many institutes like Institute of Physics Bhubaneswar, BCC, Calcutta, our institute, Indian Institute of Technology, Indore. So many institutes are involved in this Indian endeavor in ALICE. And you can see this detector is made in India. PMD, the photon multiplicity detector, and we went there, installed it, and took data and published papers. And it is not a easy game of working in multinational domain. You should have that kind of understanding, and you can go with the pace of international community. So there are many different challenges which are involved in working in multinational environments. It's not a small game. Excuse me. So this is another detector called time projection chamber. So this is there to track the charged particles. You can see a person sitting and repairing the detector. This is the scale of the detector in high energy physics we people use. If you look at the launching of the CMS experiment in 2004, the dock was completely dry. You can see this is underground 150 meters down. I have gone there to see after the installation. You will find after the installation this looks like this. Lowering of a detector of this volume, which weighs more than the Eiffel Tower, you need this kind of precision mechanical engineering that you should start thinking of. So these are actually the lowering act of huge detectors in this cavern of CMS experiment. So again, just to tell you, the Atlas and CMS experiments, each detector is like 100 megapixel camera, which takes 40 million pictures per second. The largest and most complex scientific instruments ever built by humankind are actually these frontier detectors. Let me take 1 minute to tell you a little bit about God particle before I move to the societal benefits, which is the thrust of today's talk. So the Nobel Prize in 2012 was given to Francois Enlot and Peter Higgs, and the Nobel statement says, for the theoretical discovery of a mechanism that contributes to our understanding of origin of mass of subatomic particles, and which recently was confirmed through the discovery of the predicted fundamental particle by the Atlas and CMS experiments at CERN's Large Hadron Collider. This is the place where CERN tries to take the credit because of the experimental discovery, and these two people got Nobel Prize. And present CERN Director General Fabiola Ghiattini, then spokesperson of the Atlas experiment, is congratulating Peter Higgs for theoretical conjecture which happened in 1964. So you can see why it has taken so much of time since 1964 to the establishment of these collaborations or these experiments in 1992, and finally the discovery happened in 2012, and it has taken so many years. This is also physics driven, this is also technology driven, so you should try to understand why, what does it take, once a theoretical conjecture is given today, why sometimes the technological development takes so much of time. And this is a very good cartoon which came up after the discovery of God particle or Higgs, which is responsible of mass generation at subatomic level. And the person who has obesity, the fat person, he says it is not my fault. I was born with too many Higgs bosons. So this is just a popular cartoon. So how does the Higgs field give mass? Just to tell you in a popular way. So this is a cocktail party where guests are evenly spread, and there is the arrival of the celebrity. So with the arrival of a celebrity like a movie star, film star, so or any big politician, so people usually come closer up to the vicinity. By that, this clustering happens, and with the velocity or the speed with which the person was moving, now this will be restricted, and in a technical language, the person gets some effective mass or the velocity decreases. By this, the effective mass is higher compared to the bare mass of the particle or the person. So the guests act like Higgs field, and the celebrity gains mass. This is a common or popular way of explaining how this God particle or Higgs is responsible of giving mass. So let me now take you next 15 minutes to the social benefits. Social benefits, let me start with the electron discovery. So electron microscope, you might have electron microscope in your laboratory in Padna University. You will find this electron microscopy uses a beam of accelerated electrons. Wavelength of electron is almost 10 to the power 5 times shorter than the visible light. By this, the resolving power of electron microscopes are much higher compared to normal microscopes. So we can see the smaller dimensions, for example, microorganisms, biopsy samples, different nanostructures, and this is also useful in nanofabrication. In condensed matter physics, you might have noticed that this nanotechnology highly depends on characterization through your electron microscope, your SEM, TM, XRD, and things like that. So these nanoparticles possesses different physical and chemical and biological effects compared to the bulk materials. And this is highly possible because of high surface to volume ratio. This is a physics point, and this has the ability to interact with biomolecules differently. So nanotechnology has got immense applications in optoelectronics industries also. So if you look at any small medicine, for example, the medicine Silverex, which is used with silver nitrate composition, you will find silver nanoparticles, and this is given for better drug delivery to the system. And this I show you the famous TEM image of coronavirus. So you may be astonished that in your country also the strict directive might have been given by the Ministry of Health that washing hands using soap is frequently is required because that destroys the virus. How do I know this? How your ministry knows about this? So here your basic science works in a tremendous way, and corona is a self-assembled nanoparticle with lipid fatty layers. To explain you in a better or simpler way, when you eat little oily food, you use soap to wash your hand and just to remove the oil stains. Okay, in a similar way, so coronavirus has a fatty bilayer, lipid layer or fatty bilayer. When you use soap, so that will destroy the outer layer. By this, the complete destruction of the coronavirus will happen. And this we came to know from the TM image of the coronavirus, and TM uses this electron microscopy principle. Now you can see in the days of pandemics how discovery of the fundamental properties of electron or electron as a subatomic particle and taking it to the technological domain of application in terms of electron microscope has immensely helped. And similarly, another example is Paul Dirac, who gave you the Dirac equation. So he also talked about flow of electrons in transistors. So now this is also a building block of any modern day computer. So we should note here that these are only few examples, and almost all the subatomic particles have got direct or indirect short-term or long-term social benefits. Regarding the pathway of an innovation, so in the cloud chamber picture, the first antiparticle was discovered by Carl Anderson in Caltech laboratory in United States, and he got 1936 Nobel Prize. He's Carl Anderson. And his mentor was Robert Millikan. His experiment, we do E by M experiment, or measuring the charge and mass or the ratio in the oil drop experiment in the laboratory, you do that. So Robert Millikan is the mentor of Carl Anderson. He also had got Nobel Prize in 1923. So you can see how mentor also has a big impact on the discovery. So both got Nobel Prize. So you may question now that what is the advantage of discovering this antiparticle positron or the particle, its counterpart electron. So at the fundamental level, it may not be of great importance to common man in daily life. But if you look at their discoveries, so which happened in early 20th centuries or before that, so we slowly emerged to positron emission tomography, which I am going to discuss. And again in 1932, the operation of cyclotron as accelerator happened, which produced these antiparticles. Just to take you to the frontier, what is happening in 1995 in CERN, researchers used the low energy antiproton ring layer to slow down, rather accelerate antiprotons. By doing so, they managed to pair the positron and antiproton together, making few anti-hydrogen atoms. Hydrogen atoms we know. Anti-hydrogen atoms making in the laboratory is something new. So although they lasted for very small time period, so taking the similar concept, NASA in 2000, NASA scientists have announced early design for antimatter engine. So bringing matter antimatter together through the annihilation process, they can produce energy, and that energy can actually fuel these spaceships, and a trip to Mars could be possible. And for this, 1,000,000 grams of antimatter will be used to fuel this. And NASA is in the search for or developing the essential technologies for antimatter engine. Just this is to excite you how the first antimatter discovery from cosmic rays happened in 1932, and now we are in 2020. So NASA is aiming for antimatter engine. If you look at medical imaging, you might have seen positron emission tomography, which actually is used for making tomography of imaging of the brain or looking into the cancer cells. So this uses the low energy annihilation of electrons and positrons. Here positrons are used like fluorine, which is actually used from the decay of this is created in cyclotrons from the decay to oxygen 18 and one positron source. This positron source is now injected to the human being. For example, we have electrons in our cells or atoms, and this can club together electron and positron. So with pair production mechanism, it can give two gamma rays, and you can actually look into the kinematics. So these two gamma rays will be produced back to back almost 180 degree, and two scintillator detectors will be used to detect these two gamma rays. And if I backtrace it with linear projection, so I can find out which cell has given me these two gamma rays. By this fundamental principle of using pair production and electron positron. So this imaging can be done, which is actually essential for brain imaging or many delicate imaging of cancer cells. So many detectors are used in the subatomic particle detection or got place in medical imaging. And George Charpak, who got Nobel Prize in 1992, he developed actually multi-wire proportional counters, and slowly he moved to medical imaging sector, and he was very essential. He is a pioneer in development of detectors for high energy physics, which have got place in medical imaging. And if you look at the hadron therapy, for example, proton therapy, so you will find almost 9,000 accelerators are operating around the world, and out of 17,000 accelerators, so these are actually used for medicine purposes. So this actually shows a map in Europe. You can find several particle or proton accelerators are used for medical therapy. In India, we are fortunate to have proton therapy centers in Chennai, in South India, and in Tata Memorial Center, Bombay or Mumbai. So another proton therapy center is coming up. So this will help you in making cancer treatment of cancer cells or tumors can be treated by proton therapy. So you may question now, what is the problem with treating with X-rays? For example, radiation therapy. So let me tell you, if you look at this relative dose as a depth, let's say depth in the skin, or for example, depth in the body. So if you make a cancer therapy using photons or X-rays or radiation, it has a profile like this. So it will deposit most of the energies, the higher energies will be deposited in the first cells or initial penetration, and slowly that goes to a higher range, and in almost everywhere the energy will be deposited. For example, if you have a cancer cell here, why do I need higher energy deposition in the healthy cells, which will damage my healthy cells? If you look at the Bragg peak coming from the charged particles, so you will find a charged particle will deposit less energy in in the initial phase, and once it is coming to, because the basic principle for Bragg peak is the delta E, the energy deposition is inversely proportional to the velocity square. That means around the stopping time or stopping velocity, when it slows down, it deposits maximum of energy. So I exactly calculate what depth is the cancer cell is there, and that depth calculation, what is the energy requirement, I can calculate from my simulation, and then I can actually put the proton energy or carbon energy, carbon nuclei energy, ions energy. So they can actually deposit complete energy at a depth exactly required for the cancer cell. By this, the healthy cells will not be destroyed, and only cancerous cell will be destroyed. And you can see, and it stops completely. Again, further healthy cells will not be destroyed. So this is the new technique called hadron therapy, uses the technology of accelerators. These are actually modern days, and you can, if you translate to your currency, you will find as of today, a single cancer therapy treatment in hadron therapy actually cost like 1 crore Indian rupees. You just convert it to your Bangladeshi currency, you will find it's a very costly business. So slowly, if we can have centers for hadron therapy in various countries in Asia and elsewhere, we can actually better control the cancer, which is actually growing rapidly. If you come to World Wide Web, when it was proposed by Tim Berners-Lee in 1989, his boss Mike Sandel told that it is a vague idea but looks exciting. Nothing to stop, Tim Berners-Lee went ahead, and he was able to discover World Wide Web, and this proposal actually gave birth to WWW or Internet. So this is the brass plate, so which is actually there in the CERN corridor. So I will show you that this old World Wide Web was discovered by Sir Berners-Lee at CERN, out of, so his son Sir Berners-Lee, Tim Berners-Lee. So this www was a necessity to make another experiment at CERN. This data available to his world users sitting at different corners of the world. This was the first server, World Wide Web server. And when we go for having coffee in CERN cafeteria, from our experimental, our offices, we go through this corridor, and you can see in this corridor, this plate is there, which is actually, this was the office of Tim Berners-Lee. So a simple necessity has actually given birth to the discovery of World Wide Web, or the today's internet. As you can see, I'm talking to you with a distance of more than 2000 kilometers over internet, and we are interacting with each other. So this is possible with the blessings of basic science, or the outcomes which have come from high energy physics. So this is the CERN corridor building. So science is not patented. As you can see, the CERN authority decided that so with this statement, CERN told that CERN relinquishes all intellectual property rights to this code. Both source, binary form, and permission is granted for anyone to use, duplicate, modify, and redistribute it. So this kind of scientific leadership and not patenting this kind of discoveries are very, very important for human beings or the mankind. I will give you another example. When Faraday discovered electricity, he informed William Gladstone, the British Chancellor of Exchequer, the Ministry of Finance. When the minister asked about the practical value of electricity, so Faraday replied that one day, sir, you may tax it. So government is always interested in, or finance ministry is always interested in taxation, increasing, the physical reserve of the government. So when Faraday replied that one day you may tax it, you can see, that may be a joke, but you see, if at all we have to pay for electricity or for internet to Tim Berners-Lee. So you will imagine, if one click of internet, you have to pay tax to these discoverers or inventors of electricity and internet. This will cost a lot. And taking this kind of scientific leadership is very important, that this should not be patented. This should be left to the common use. So here I would emphasize that scientific leadership in each country, able leadership is very, very important. So each time one types HTTP or www, one unknowingly pays tribute to CERN. This is written by CERN ex-DG Harwick Schopper. You see, this was the biggest spin-off of Collider experiment. Large data sample, huge number of people involved in the experiment, multi-country participation, and the need of data access to all. A common goal of doing world-class physics are the frontiers of physics at fundamental level. These were actually the necessities which driven us to go to these frontiers of science and come up with the spin-offs or contribution to the humankind. Like electricity, internet is now in each and every home. In the bad days of COVID-19, www is of immense help in reaching out people, contact tracing, information exchange, administrative management, scientific collaboration in developing vaccines, and exchange of ideas, how quickly we can come up with a vaccine, online teaching and lecturing, which will go on for some time now. Everything is now dependent on internet. So you think now, what is the implication of this basic science and doing physics at its frontier? This is the internet map. As you can see, it is highly populating with time. This is the world map of internet. Almost everybody is using now internet. Another more application, I'll take maximum 5 minutes of yours. I started to, I thought going slow, giving the message to everybody will be very important. That is the reason, let me take a couple of more minutes to convince you what are other applications, maybe without going to very details. So grid computing is another new age computing. Sitting here in my home, I can actually submit my job for data analysis in these experiments, and the protocol executes my job in US, any server, or in America, or in Europe, or in South America, or South Africa, any servers like you can see in this map. So once the job is submitted in these servers in the distributed computing in a grid way, so then I get the output. Whatever I might have got in my laboratory or the institute computing centers sitting for months and months, I get it done through grid computing in couple of hours. This is the tremendous new age of computing which has emerged through these high energy nuclear physics experiments. Going to touch screen, which everybody uses now, Frank Beck and Ben Stumpe, engineers from CERN, they developed a transparent screen in early 1970s, and the touch screen was manufactured in CERN, put to use in 1973. So you may be astonished in CERN while working on these things which are actually requirements for our kind of doing science. Industries have given ample ample amount of help in developing things further, and with time many new touchscreen technologies have evolved like capacitive, resistive, and we are in a domain that our watch, if you look at different smart watches, so you have everything, how much steps you have taken, what is your heartbeat, what is happening to your corona infections, if you have an app of that kind, if a mail is coming, a pop-up will come. So many things are now you can put actually in a smart technology era just in your watch also. So this era of smart technology have evolved again through different kind of researches at frontier level. Some more social benefits, aerospace applications, applying physics to financial markets, and electrochemical sensors for water pollution measurements, controlling environmental pollutions, software solutions for automated driving, general aviation safety, medical imaging, and space dosimetry. These are actually few domains. Our high energy experiments are parallelly involved in different kind of societal benefits or collaborative works. So before I stop, in couple of slides, let me tell you that ALICE is a big experimental collaboration, almost 1975 collaborators, 41 countries, and 177 institutions. India is a big stakeholder, almost 45 scientists and 10 engineers. We are working with more than 50 PhD students and several institutes, almost 13, 14 institutes. My own Institute, Indian Institute of Technology, Indore is also involved, and it is generously funded by our Indian government, Department of Atomic Energy and Department of Science and Technology, and we work in the frontier of subatomic physics through this involvement, and almost you can see India is now a leading country in this subatomic physics. Again, just to show a couple of pictures, we are involved in detector development. This is another detector which was manufactured in Sahoo Institute of Nuclear Physics in Calcutta. We came up with different multiplex signal processors, common readout circuits, and then the upgrade proposal for silicon calorimeters and grid computing we are involved. And this is a picture I saw which belonged to almost 2005, where I was also instrumental in soldering and making these unit modules at Institute of Physics Bhubaneswar, which were installed as a part of the big super modules, our proportional counter detectors in Brookhaven National Laboratory. And I must tell you, it is a glorious phase in academic life or scientific life to participate in these international endeavors, make detectors, put it in high-end laboratories, take data, interact with international community. And I am proud to tell you today that as a high-energy nuclear physicist, I have enjoyed my life doing both detector fabrication and testing, writing physics papers and guiding PhD students and leading a team of scientists from IIT Indore, contributing in an immense way to basic science. And a way forward, if you see, there are several laboratories, accelerators coming up in various scales worldwide. you will find that the GSI laboratory in Darmstadt, Germany is coming up with a next generation accelerator, which is fixed target. EIC, Electron Collider. So this accelerator is coming up in Brookhaven National Laboratory, US. India is involved in both the laboratories. And this is a Russian laboratory. And this is again 100 kilometers future circular collider is being planned for next 20 years, coming up in CERN, Geneva, Switzerland. Again, India will be a participant. And again, in the way forward, we have International Linear Collider, a next generation megascale particle accelerator. This may come up in Japan, Europe, or USA. The place is not decided. But just to compare, 3.2 kilometers slack Stanford Linear Collider to 500 GeV accelerator or 1 TeV accelerator, which is actually will be 30 to 50 kilometers long electron positron collider. China has also a 80 kilometer circumference electron positron collider coming up in some place. And finally, I should stop here. I guess I could convince you what is the necessity of doing basic science, developing technologies in a symbiotic way. And finally, scientists, if you ask questions, yes, we have answers to some of them, and the whole universe is a bigger scale. We have not understood many things. That is the reason scientific endeavor is still on. And in my last slide, let me quote Michael Faraday by saying, nothing is too wonderful to be true if it is consistent with the laws of nature. And let me put up a statement here that precision science and technology is the call for next generation science and technology. So for the next generation, precision science and technology is a requirement, and the discovery should happen in 6th, 7th decimal places after the, yeah. And finally, I thank you very much for having patience to listen to me almost 1 hour plus or 1 hour 15 minutes. And I guess my job of convincing you and giving you a glimpse of societal benefits of these large scale experiments is I could do it to some extent if I could convince you that doing this subatomic scale physics is a requirement, it's a necessity of basic science and having tremendous applications in modern day technology. So I have done my job. Finally, thank you very much. Namaskar to all of you.
Thank you, sir, for your wonderful lecture. I think students have enjoyed your lecture and learned a lot of things. So if you allow me, then we can start our discussion session.
Sure. I think I have not bored you, taking a little more time.
No, it's okay, sir. Yeah. So we have got some question in inbox and in comment also. So so one student actually asked, so can we create the same situation in CERN like Big Bang? Is it possible?
Yeah, actually, as I explained to you, exactly, we are doing a similar kind of situation in the laboratory in a smaller scale, of course. So like heavy nuclei, the diagrams I showed you, we collide almost 99.99. Again, you can put another more nines there. So that much of speed of light, we are actually colliding the heavy nuclei and creating a scenario which might have been created at the early universe after few microseconds of the Big Bang, and the temperature was very high. Then we look into the matter evolution in a nascent way, which might have happened in a natural way. So that is what we do every day in the laboratory in RIC, in Brookhaven, and also in CERN.
Thank you, sir. So we have another question. So we know that we got quark gluon plasma in early universe. Can we create quark gluon plasma in our lab? Is it possible to create quark gluon plasma?
So it's possible, as I could convince you. So these quarks and gluons, they have not got a independent existence because of the very nature of the strong interaction, and these colored particles follow strong interaction. And without stopping at that point of time, so the scientists started thinking that possibly we can create a plasma where in a higher domain like hadronic domain, these quarks and gluons can be free, for example, in a nuclear domain. So that is the reason we have started colliding these heavy nuclei in the laboratories, and the energy requirement is up to TeV scale, and TeV scale accelerators are only possible with multinational collaboration, because multi-billion or million funding requirements are there, and huge technologies. Each detector is having a technology by itself. That is the reason multinational collaborations. For example, our Indian detector, when we started making it, so that almost took 10 years of conceiving the idea, doing the R&D, making the simulation, prototyping, testing, and then unit module fabrication, your super module fabrication, transporting or commissioning in Brookhaven or US, Brookhaven laboratory in US or in CERN, and then taking data. So this usually takes a good amount of time. And why so much of money involved? Why so much of manpower involved? Multinational cooperation is involved. It is purely physics driven. Okay, usually people comment, you see, so many people are involved in the experiment, but believe me, it is driven by physics. I explain you. Again, I can explain you from small equations like E is equal to mc square, your lambda is equal to h over p, and E is equal to kt. These beautiful small equations will explain you why so many people involvement is a requirement.
Okay, thank you, sir. So we have another question. So is there any influence of electric field or magnetic field on photon?
Photon, as you know, it is a neutral particle. So neutral particle cannot be influenced by electric field. And also you cannot bend it in magnetic field, because we also know from our textbook, for example, electricity magnetism book, so we know it is not possible. But once this accelerated charge particles bend in the presence of magnetic field, we create synchrotron radiations, and those radiations are actually different energies. Photon radiation, by photon, this we know as this gamma rays or X-rays.
Thank you, sir. So we have another question. So for scaling mass, what should be done? How can anyone predict the actual mass of this subatomic particle?
Yeah, so if you look at the mass prediction, or you see, how do we see the discovery? So we will only at the detector level, we'll only have a glimpse of the final state particles. So if we look at any particle discovery, for example, you take Zephyr or Higgs, so theoretically we have to know in which decay channels they will come, and then we have to make an invariant mass reconstruction. Okay, so taking the energy momentum information of the final state particles, then they may appear like a Gaussian peak, okay, in the invariant mass spectra. So these are actually little technical stuff in the data analysis, but for more, I think you can Google it to know so which way this will come as new particle discoveries. But theory also helps us, and experimental techniques are also now quite helpful in the discovery of subatomic particles, and we have complete handle on the energy momentum and particle identification in the subatomic level.
Thank you, sir. We have another question, sir. Can you say something about tetra quarks? Is there any experimental proof exist in support of tetra quark
Yeah, I think
combination?
it is a beautiful question. If Rakesh is already exposed to this kind of domain, I will be happy. This tetra quark, pentaquark, these are actually composites. These are not actually predicted by standard model. So standard model prediction is either 3-quark combination, which is a baryon, or quark antiquark combination, which is a meson. And this tetraquark and pentaquark, these are actually beyond standard model. These are not within the standard model predictions. So these are actually called different composite objects like exotica. So people are also looking for this exotica. Either it is a molecule of, for example, if I talk about pentaquarks, or for example tetraquark, is it a meson molecule giving you tetraquark, or pentaquark is a molecule of a baryon and meson? So that is actually of a frontier research. For example, Bell experiment in Japan and different experiments in Alice has also, our experiment has also gone into looking for these tetraquarks and pentaquarks, glue balls. This exotica search is on, but experimental proof, is it a single composition or single entity of tetraquark, or it is a molecule of meson with meson, is not yet completely resolved. This issue is still there. So research is on. It is quite frontier, and I am quite happy. Thank you, Rakesh, for asking this question. And yeah, thank you very much.
Thank you, sir. We have another question. So, sir, while melting the quarks, we need to so much temperature. In laboratory, which source provide us so much temperature that can be melt the quarks?
Yeah, we are actually not melting the quarks. Let me little correct you. It is melting up the hadrons. For example,
Yeah, yeah.
protons and neutrons, those are actually constituents of the nuclei we are colliding with, right?
Yeah.
So let's say if you are taking lead on lead, which is taken in CERN, or gold on gold ions. So we strip out the nucleus. Strip out means completely stripping out the electrons, so that the charge state is higher, right? So
Yeah.
once charge state is higher, it is almost, I'm not recalling the numbers exactly. I think it is 79 plus for gold and 82 plus for lead. One can check it. So then acceleration becomes easy. And once acceleration becomes easy, so the constituents are actually your protons and neutrons. And protons and neutrons, neutron is a neutral particle which is a free rider. You give energy to protons, but electrons as a composite, they are free riders. They are sitting inside the nucleus. So we take it to very high energies, then collide. And once this collision is happening, so this produces huge concentration of energy and temperature is huge. So in fact, our experimental observable also tells us direct photons coming out of this experiment. So this also tells us that almost 10 to the power 5 times higher the core of the sun temperature we are producing. This can melt the hadrons, and it can produce a soup or plasma of these quarks and gluons, which are primordial matter. So maybe if you are more interested some other time, I will show you physics plots from our examples. So this will be little higher compared to this public lecture, but that
Yeah.
can really convince you how we can apply statistical mechanics, which you study in our textbook, to get the information about temperature and other things of this primordial matter. Thank you, Nadim.
Yeah. Thank you, sir. So we have another question. So what is the hadron gas phase? You have actually explained maybe in your lecture and
Yeah.
showed the picture. So one
So I
student.
think my screen sharing is still there. So
Yeah.
let me go to that picture which actually better depicts. Yeah. So here is, if you see, so what is happening is, so as I told you, so these two heavy nuclei will be Lorentz contracted in the longitudinal direction, the beam direction. After the collision, there is a soup produced here. So this soup is a soup of quarks and gluons, which are the primordial matter, and they are actually very short-lived. So if you make a Google search, you will find strong interaction lifetime is 10 to the power minus 23 seconds. So they will immediately make the composites which are called hadrons. So once these hadrons are made, so they will make a gas of hadrons. Gas or liquid, so we do not know. We have to probe it. So let's assume that this is a gaseous phase of hadrons. And the composites will be these pions, kaons, protons, all these things. Okay. And once this is an expanding system, because a high temperature system will expand. Once it is expanding, so what will happen is, so slowly their mean free path will be higher compared to the system volume. So they will not collide with each other. At that point of time, so we detect these things in the detector as particle tracks in the detector. Okay. And to answer your question, what is hadron gas? It is a gas of these composite hadrons, which are pions, kaons, and protons.
Thank you, sir. So we have maybe the last question. So is there any example where particle is produced from only energy?
Yeah, it's a good question. Yeah. So you see, I have initially collided, for example, proton with protons or heavy nuclei. And as I told you in the previous question, the constituents are protons and neutrons. If you look at quark level, the constituents are UUD or UUD quarks. Essentially, the first generation of quarks will come as the constituents of the matter, normal matter, UD. And if I produce a kaon, for example, so it has strange quark as the constituent. How strange quark is produced? If I ask you the question now, initially the constituents are not carrying strange quarks. So if the strange quark is produced, it has to be in the platonic phase and it should come out of energy. So because we have given a huge amount of energy is concentrated, and out of that energy, so the particles are produced. So at the quarks and gluon level, your quark annihilation process, gluon fusion process, so these will give rise to different composite objects which are not seen in the normal nuclear matter. And indirectly, this has come out of huge concentration of energy and through these collider experiments. So this energy is responsible for producing matter.
Thank you, sir. So I think we have finished our questions, so we can conclude this discussion session. So thank you, sir. As we know that you are too busy with your research, and we have already come to know from your lecture that you have done a lot of things like research, lecture, online seminar, webinar, and still you accepted our proposal. And we actually very glad to actually host you. And I would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology. So thank you, sir. And hopefully we'll see you again, because you have told me that you are very eager to talk another lecture for our students. So thanks for that also, sir.
Yeah, that can be little higher level going, this taking this at the platform and moving little ahead with physics plots, how we characterize using our classroom or the textbook knowledge. So I am also thankful to you giving me the first exposure to talk to my loving neighboring country, Bangladesh, who is actually, I wanted to visit once to give a lecture in a school.
I will arrange after this situation is over. So some student actually, but this question is out of this lecture. So is there any opportunity for student to admit for masters or PhD in indoor IIT, and what is the procedure for that for outsider? So students from Bangladesh, other country.
Yeah, actually, I find, because our IIT is 10 years old, and compared to other older generation IITs, we are second generation IITs, and there is a scheme for foreign students. I could find the students from Thailand and couple of South East Asian countries, and exactly, maybe I will make a correspondence with you what is the procedure of admitting. And we have those schemes, and particularly in IIT Madras, I find many students from South Asia, and IIT Bombay, Kharagpur must be having those numbers, and slowly second and third generation IITs are also building up, making an international forum that we admit any student from any part of the globe. And I guess you can know from our webpage. I do not know exact procedure now, so I can make a correspondence with you, and I welcome more student participation or learning from IIT Indore. And we are an emerging institute with very high ranking, both globally and in India. And hope we'll do our best and provide all our resources for the benefit of everybody. Yeah, thank you very much.
Yeah,
and
thank you
for hosting the talk. Thank you very much.
Yeah, thank you, and see you again. Namaskar, sir.
Yeah, namaskar.
Bye, sir.